hope my screen is visible to all of you.
Yes, sir, it is visible, sir.
Okay, so welcome everyone to the 11th tutorial on materials characterization. So in the last class, what we did, we started the introduction to transmission electron microscopy, and we went through the instrument part, like what are the different types of instruments, the components there in the transmission electron microscopy, and from starting from all the way from the top to the bottom, we saw that there are complicated lens system is there in the transmission electron microscopy, and also what are the requirement, what are the different types of holder, what we saw that we put into the sample chamber, the electron gun column, and then accordingly we saw that we get some kind of output is either we are getting in the form of image or we are getting in the form of diffraction pattern. So continuing on that, like last class we mostly studied about the instrumentation part. So today we are going to study a little bit about how the interaction is happening, like the electron and our specimen interaction, how is it happening, and the physics behind that, as well as for how to interpret the images, like we are getting the final images, and how to interpret all those relationship that we are going to get from our different types of images and patterns. Okay, so before going there, I want to clarify regarding the bright field and dark field imaging. So in the last from the previous weeks, we are continuously saying that there are two types of imaging that we do generally. One is bright field imaging, another one is dark field imaging. So what is the point, like what is the mechanism, if we want to understand that thing, then so here I have given three examples, option that means the scenario A, scenario B, and scenario C. So now we will see what do I mean by bright field imaging. So bright field is, as you can see, let's say this is my specimen. So now I am talking in terms of my specimen is in the TM chamber. TM chamber means TM chamber is always evacuated. So if my specimen is in the TM chamber, let's say this yellow color entire thing is my specimen, and here the optic axis you can see, right? The optic axis you can see it is coming down, and here the incident electron beams are coming, as it mentioned here. So once the incident electron beams are coming in the specimen, if you can see, there are some black type of solid lines are there. Those solid lines are nothing but planes. So this plane may be any oriented, so I will say them HKL plane. So indices of those planes are HKL. Okay, so these are the real space planes are there, and they are since our electron beam is coming and the planes are not perfectly aligned according that is not a zero angle. So with in some angle, some incident angle theta, it is coming, and it is being incident on our sample. Now let's say the Bragg's condition is satisfied, that means the diffraction condition is satisfied. So if the diffraction condition is satisfied, which is n lambda is equal to 2d sin theta b I am writing, that means theta b is nothing but the Bragg angle. So these incident beam are coming and interacting or getting diffracted from this Bragg's plane are nothing but HKL, and then they are giving different types of beam. So when my incident electron beam is coming and interacting with my specimen, there are two scenarios that can happen. One is some of the electron beams will not interact with any of the planes, because those planes will not be oriented in that direction, or they might be simply going undeviated. So those beams will be called as direct beam or undeviated beam or undeflected beam. So many names we can see throughout the different textbook. But the second scenario is these incident beam will be interacting with the Bragg's plane. When I say, that means these electron beams will be interacting with the getting diffracted by the corresponding atoms which are staying in those Bragg's plane. So when the interaction happens and when the diffraction takes place, so there is second scenario that takes place, that is called as the diffracted beam, right? So now as we can see, so two types of beams are coming. Now if I want to collect all the beams, let's say I want to collect direct beam, I want to collect the diffracted beam as well. So if I want to collect all two beams, then in the end what will happen? At the end I will not be getting a, I will be getting an image, right? So those images that all those images will be consisting of information. Those information will be carried out by both the direct beam as well as the diffracted beam. So I will not be able to distinguish that what is this information is all about. So that is why there is an option for us to keep an objective, an aperture. So where we are keeping the aperture, let's say I am keeping the aperture for in my objective lens system. So in the objective lens system I am keeping an objective aperture. So what is the job of the aperture? The role of the aperture is to block the unwanted beam. In this case, what is my unwanted beam? If I am considering case number A, what is my unwanted beam? I do not want any of the diffracted beam to go and hit the to go and pass through my objective aperture. Aperture means it is a some kind of slit with a very small hole. Okay, through that hole the beams will pass. So in case number A, so what is my objective? My objective is to I want to place my hole of this objective aperture in such a way that only the undeviated beam or the only direct beam will go and hit the specimen, right? So in this scenario, if I say that if only the undeviated beam are going and hitting the specimen, that means whichever beams are going now and hitting the specimen, if for a moment consider that there is no specimen, for a moment consider that there is no specimen. So without the absence of specimen, this entire, let's say this is my screen, without the absence of a specimen, this entire screen will be turned white, right? This will be turned white or bright. Why? Because all the direct beam are coming and hitting my screen, okay, the screen of my detector, right, without the absence of specimen. Now in the same scenario, what you do, you put the specimen. So what will happen? The direct beam will be still forming my direct beam will be still hitting my detector or hitting my screen. However, now that these there are lots of planes are there are lots of diffracted beams are there. So what will happen? Some of the beams will not be able this detector will not be able to collect, or the screen, some of the beams will not fall onto the screen. So there you will get a dark feature. Why you will get a dark feature? Because surrounding this one, I'll change the color little bit. So surrounding, so let's say this, there is a round color structure is there, right? So there is a round color structure is there in my material. So and this round color structure is giving a diffracted beam, and those diffracted beam is not able to pass through the aperture, right? So but the surrounding of all that feature, let's say that circular feature or that spherical feature, since it is giving the undeviated beam or it is giving the direct beam, so from all the other features surround, which is all the other areas which are surrounding this round color feature of in my sample, they will be forming it here. All those beams will be coming and hitting your sample, right? Or sorry, not sample, the screen of your detector, right? So all the surrounding, from entire surrounding, my undeviated or the direct beams are coming and they are getting formed. Only this portion, it is like a concept, you can it's not exactly, but it is some sort of similarity you can see, you can some sort of similarity you can assume as compared to the black hole. Like we know that we can't see anything when we put our light into a black hole, but how do we know that this is the shape of the black hole? Because light bends around its horizon. So similarly, based on that feature, we are able to see that okay, this might be the size of the black hole. Otherwise we are not able to we cannot see, right? So it is similar theory, not exactly similar, but is so same kind of comparison we can do, that we are getting light surrounding this black region, black circle which is present in the crystal or which is present in our specimen. However, we are not getting any kind of light from this feature. So that is why the feature will always appear dark, and the background where all the light are passing and it is getting collected by the screen of our detector, which is staying below the transmission electron microscope. So that will appear bright and this is going to appear dark, right? And this is what we call it as bright field imaging. Okay, same thing now if we do for same thing we want to do, but we want to reverse the reverse the position of the aperture. Now for me, now let's consider case number B. Same thing is happening. It is the incident beam is coming, the electron beams are interacting with the specimen. Now what I want to do, I do not want to consider this direct beam anymore. The direct beam for me now has become unwanted beam. So I will place my aperture, the objective aperture, in such a way that the hole should be allowing all the diffracted beam in my the diffracted beam to through this aperture. So now that all the diffracted beam are coming and all the diffracted beam are coming and hitting, it is getting collected by the screen. So what will happen? Your without the specimen, if you want, without the specimen, for a moment you just remove the specimen, so you are not able to get anymore the direct beam. That means the entire screen will be now dark because you are not getting the direct beam anymore. So this entire screen will be dark. So when you are allowing the diffracted beam now from using the objective aperture, so those beams will only carry the information regarding the, let's say this feature is regarding a circular feature which is there in the material. So that means whichever information you are getting, whatever beam you are getting, so those beams, when you combine all those beams on the screen of your detector, those beam will be giving a bright feature. Okay, because only from this area of the sample you are collecting beam, rest all of this area you are not able to collect the beam. So that is why your background will be always dark and your feature, that is always bright, and this is what called as dark field imaging. Okay, so remember, the bright field and dark field always refers to the background. Okay, so bright field means background is bright and your sample is dark, and dark field means background is dark and sample is bright. So you should remember you should know the fundamental mechanism behind this about bright field and dark field. Now there is a special case in the case number C. So case number C, why we consider? Now the thing is, when we want to see, we can do either bright field or dark field, but the problem with dark field is, since electron diffraction is very sensitive to aberration, like electron beams are very sensitive to lens aberration. So what will happen, the moment you collect the sample from these regions, let's say you collect the beams of the you collect the diffracted beams, then what will happen, the more these beams are going away from the optic axis, the optic axis is this one, the more these beams, diffracted beams, are going away from the optic axis, the aberrations will start increasing. Why? Because the aberration is a function of alpha, right? Alpha is the semi-convergence angle. In the last class we saw that. So these aberrations will start increasing. It will be not much, but still it will be significant to for us to misinterpret the images and the information. So that is why what we did, we said, okay, we will not so the moment we are collecting this information, collecting all these beam away from the optic axis, that is the reason that these aberrations are coming, right? What we will do, now we will tilt the incident beam. Okay, so now the beams are coming a little bit tilted. right? Since the beams are coming little bit tilted, but still remember the optic axis is staying as it is. So the optic axis is staying as it is, the beams are coming little bit tilted. Now for these tilted beams, these are all the what? These are all the undeviated beam, or these are all the direct beam. And after interacting with the planes, those are here. These beams are the diffracted beam for this tilted beam. So when this phenomena takes place, I do not want to when this phenomena takes place, I do not want to move my aperture. Now my objective aperture can be on the optic axis. Earlier case, what I was doing, I was putting my objective aperture away from the optic axis, right? So this is optic axis. Now my objective aperture is along the optic axis, where it is allowing all the diffracted beam to be collected. So in this case, my diffracted beams are coming on the optic axis. That means I have reduced the amount of aberration and that I was getting from the previous case, right? And this is this kind of imaging. So here also, since I am only collecting all the beams from the diffracted planes, so this is also the background will give me dark. Okay, so this is also another type of dark field imaging. The background will be dark and these features are still bright. But since the position of the dark field, the position of the diffracted intensity are in the center, so this kind of imaging is called as center dark field imaging, or in small in abbreviation this time this is called as CDF, center dark field imaging. Okay, so these are the three different cases of bright field imaging techniques. One is bright field imaging, dark field imaging, and center dark field imaging. Comparing to that, so here what I have taken, so now there is another case where we will see it here. Earlier what we used to do, we use the parallel beams. Always we use the parallel beams. Now if I want to let's say I want to use very convergent beam, then what will happen when we do the convergent beam? I can put my detector at any point. So detector means based on the position of my objective aperture. So if I do if I put my objective aperture here, right? So for me, so for this entire segment, this will be beams will be collected, which they are known as the direct beam. Okay, so direct beam means I will be getting bright field imaging. The moment I do not want this direct beam to collect, and I want the diffracted beams, like here I'll put it in another color. So I want all these beams to be collected. So these are called dark field beam. Since when so here I am showing you on a two-dimensional from the side view, but if you want to look at from the top view, right, from top view, if you want to see, then this pattern will be looking like somewhat this. Okay, and since you will be getting so it's a hollow kind of structure, you will be getting concentric rings. Why you will be getting rings, that I will explain in a subsequent slides. So since this kind of imaging you will get, see here, this is dark field. Okay, background is dark, this is a diffraction pattern, but okay, let's here. So this is an background is dark, however all the particles that are here, they are bright. So this kind of imaging it is called as, so DF. So this ADF, AD is annular. That means in an annular kind of structure you are getting dark field imaging. And if you want to do even higher angle, that means sometimes what will happen, some weak defects will be there inside this material, defects will be there or dislocations will be there, they will not be able to diffract that, they will be able to diffract too much. Okay, so they will be able to diffract this incident beam too much. That means in this direction, let's say there is a certain angle is associated with those thing, so they will be diffracting very at a very higher angle. So those kind of thing will be called still ADF, annular dark field image. However, since their angle of diffraction is very very high as compared to normal ADF, those things are called as high annular dark field, or simply in abbreviation HAADF. Okay, those images, those type of operation we call it as hard F imaging. okay, high annular dark field mode. So you can see this is a dark field image here where the background is dark and the samples that you are getting are white. Okay, so this is all the information that you need to know about. And this high angle annular dark field, there is a certain angle associated with it. I think if I am not wrong, then greater than 10 millirad if you are getting, then the diffracted, if this angle is, then I think this is related to high angle annular dark field. Okay, so these are the some of the concepts that we have to know before going into the TM interpretation and the physics of the interaction. So now coming to the diffraction in TM. So last class we stopped here from the image that we, so this image we stopped at this image. So what happened, the incident beam comes and here is the specimen, as you can see at the top of this at the top of the this picture, but the specimen is in the somewhat middle of the transmission electron microscope. So how we can, so I told that we get two different types of output from a TM. So one output is diffraction pattern, another output is image, right? So in which condition we are getting diffraction pattern and which condition we are getting our final image, we will just see. So before going to see that, just this is just look at this schematics, this path which are coming. So we saw it during our electron optics introduction class. So here the thing is, let's say this is an image, this is an object and one lens is there. So this is a back focal plane. Back focal plane means this lens will focus all the rays that are coming through, going through this lens to this plane, around this plane. Okay, so this is the fundamental and this is the image plane. So we know that for from Abbe's criterion, so for the formation of an image, all the rays or at least two rays coming from one place should meet in the image plane, right? So that should be the criteria. Since in the back focal plane, the at least two of the rays which are coming from the same place from in the object plane, they are not meeting there. So here they will not be able to form image in the back focal plane, rather they will be forming some kind of spots, right? So this is how we are getting spots in back focal plane, and these spots are coming from which so these spots are are getting formed by which rays? The rays which are coming, the similar type of rays which are coming from different position in the material. For example, if I am talking about let's say how the diffracted spots are getting formed over here in the back focal plane, you can see all the parallel planes which are coming from three different points. Okay, let's say O1, O2, O3, all the parallel planes, if you can see, they all will be focused at F1. All the straight, if this kind of planes you are seeing, they will be focused on F2, F0. And again, all the parallel rays which are going down, they all will be focused on this one. So if we can keep an aperture on this plane, that means on the back focal plane, and we are not allowing at the back focal plane, what will happen? At least two of the rays which are coming from same points, if I am telling that this is my ray 1 and this is my ray 2. Okay, so this is my ray 1, this is my ray 2. If I am saying, then all at least the ray 1 and ray 2 are not able to meet in my back focal plane, right? So ray 1 is at least here, and then ray 2 is going here, right? So in back focal plane they are not able to meet. So since they are not able to meet, they will not form an image. So based on this criteria, what we will do, we try to get the diffraction pattern and the final image in TEM column. So what do we do? If let's say I will put an aperture, okay, I will put an aperture in such a way that here I will put an aperture in such a way that all of these rays which are getting formed, which are getting converged in the back focal plane, I will allow all these rays to go, and only I will project these rays somewhat to my detector. okay, somewhat to my screen. Only these points I will allow. I can do that. So if I will be able to do that, what I will do? So here you can see all these points are getting formed. Okay, since all the points are getting formed, I did not allow all the rays to be deviated more and then form an image. So what we did, we allowed we put our aperture in such a way that those aperture only allowed the rays which are forming this point on these spots in our back focal plane of the objective lens. So if I do that kind of combination in the final image, because ultimately, let's say I am putting some kind of aperture here, ultimately I am allowing all the rays which are going to form a spot. So I am taking, allowing all the rays which are going to form a spot. So let's say I am putting all these things at a screen here. So if I am going to put all the if I am going to put the screen here after I allow all the rays who have formed the spot, so in that scenario I will be getting the diffraction pattern. Right now, if I what do I do now in the other case? If I do not put this aperture, let's say I do not put this SAED aperture, then what will happen? All the rays earlier I used to put the SAED aperture such as like this. Okay, so I was not allowing all the rays to go and form an image. So in that case I was getting a diffraction pattern. Now what I did, I will remove all this SAED aperture. That means selected area diffraction aperture. So when I remove this selected area diffraction aperture, that means I am allowing all these rays, that means this ray, this ray, this ray and this ray, whichever these four rays earlier I was blocking using the selected area diffraction aperture, now I allowed all of them to go and form the image plane. Okay, the moment they all the rays which are coming from the object, they get assembled at the image plane. So if I put a screen after that, using screen I will put, and after that I will put some projector lens or intermediate lens system, then the final data that I will get from the screen will be an image. In that case, so my selected area diffraction aperture is removed. And if objective aperture, why I put the objective aperture? Because I may not want to collect all the beams, like some beams will be, let's say, deviating too much. So for that reason only I have kept objective aperture. It is not to block the rays which are creating spots here. Okay, so it is only to filter out unwanted or extremely deviated beam. So when I do that case, then in that case I will be getting the image. Okay, so this is the fundamental behind the formation of an image and the formation of a diffraction pattern in TEM. Okay, so now that we have spoken so much about the diffraction pattern, let's see what is a diffraction pattern or DP. And before knowing that, so we will know that why we are actually going to obtain a diffraction pattern. So the primary reason is its ability to determine crystallographic orientation, and that orientation, local crystallographic orientation, and the level and the scale up to which it is able to get that information is in the order of nanometer level. So nowadays, with the help of even advanced transmission electron microscopy, we can even go to angstrom level. So the crystallographic like the diffraction pattern usually gives us information about the crystallographic orientation, about the interplanar spacing, about the space group and the symmetry that is associated with a lattice system, and the different the phase analysis we can do, and the chemical the phase analysis we can do, and orientation relationship also we can determine. So that is what the diffraction pattern enable us to do. So that this is the reason that we always choose to get a diffraction pattern along with our image, and then finally try to interpret it. So how the diffraction is taking place, first of all, so that we should know. So the diffraction is taking place, let's say, looking at this image, I can say that the planes, the atoms are situated in a plane. So and the distance between them, let's say interplanar spacing I am talking about, is d. Then you can see that if I am saying that my incident wave vector is wi, that means the incident is wi and the diffracted is wd, right? So it is coming in this direction, my electron beam is coming in this direction, and then finally it is getting deviated in this direction. So if my the wave front that I am talking about, it is wi and this is wd, then so then the vector which turns my wi wavefront into wd wavefront, that is known as, so that is known as, we have discussed it in X-ray diffraction, so that is known as the scattering vector, right? So similarly I have just shown the ray diagram here. This is the real life, the real scenario where the electron beam is coming. Let's say the atoms are situated in this two planes, atoms are situated in these two planes, and then incident electron beam is coming and then getting diffracted, or more importantly at this case I can say getting scattered. So after scattering, if it is observing the rule of diffraction, then we can say that the wd, these are the wd wavefront. So there, that is why whether the atoms are scattering in phase or so whether they are diffracting, it depends on the scattering, right? And whether the atoms are scattering in phase, that depends itself on the angles between the incident beam and the diffracted beam. That means this angle they are dependent on, okay, whether this angle is satisfying the Bragg's condition or not. So showing this ray path, if you can see that ki is my wave vector for my incident beam, kd is the wave vector for my diffracted beam. So I can determine this k. Okay, here I have written k, and X-ray diffraction I have written it as q. Q is nothing but the scattering vector. Okay, so here if you can see how to determine the value of k, we have seen it earlier, and this 2 theta is nothing but the scattering angle. 2 theta, theta is not the scattering angle in this case. In this case I have taken 2 theta is as my scattering angle, right? So if I am considering that this thing is happening and the scattering vector, it is the scattering vector, so what is the condition for diffraction? The scattering vector in this case k should be equivalent to the reciprocal lattice vector, then only the condition of diffraction takes place, and then I will be able to get the diffraction pattern. An example of the diffraction pattern is shown here. So what do you see in this diffraction pattern? So there are some of the distinct features that I can see when we see this diffraction pattern, that there is a bright spot around, there is a single bright spot associated with this. Okay, after this bright spot I can see there are lots of small bright spots are there. So one will be extremely bright spot, associated with it or surrounding it there will be different small or large bright spots will be can be seen from the in this diffraction pattern, right? So this is a distinct feature. This is a typical diffraction pattern that we generally see. So this is what a diffraction pattern. Okay, and we abbreviate is dp. And since it is this diffraction pattern is obtained from an area, so that is what it is called as selected area diffraction pattern, because your sample will be too big. Okay, sample whatever sample we are putting in the TEM, it will be too much big. So from that, let's say this big sample is there, so we will be collecting diffraction pattern from a very small area. That is why it is called as selected area diffraction pattern, SADP, and this process is called as SAED, selected area electron diffraction. Okay, so this is a typical electron diffraction pattern, right? And now coming to the electron diffraction pattern, here I told you that this is the electron diffraction pattern, but this diffraction pattern corresponds to, only remember there will be one big so here there are different types of spots are there, one bright spot is there, and there are different types of diminished spots are there. So this diffraction pattern corresponds to pattern of single crystal. Okay, so this corresponds to a single crystal diffraction pattern. Now there are also other types of materials are present in our material system. So if we are going to see those patterns, when we are going to see their diffraction pattern, then this is the diffraction pattern for polycrystalline material. Okay, so single crystal diffraction pattern will be only consisting of spots. Why spots? Because the we know that all the three-dimensional plane will be, so this in this diffraction pattern all the three-dimensional planes will be represented. Since diffraction pattern we we get the diffraction pattern in reciprocal lattice, so all the points in the reciprocal lattice will be referring to a plane in three-dimensional plane in real space, right? So that is why that was the single crystal electron diffraction pattern. Here polycrystalline is there no. So how you are getting the polycrystalline diffraction pattern? As a, you can see that in the polycrystalline diffraction pattern there is one bright spot is there as usual, right? Means this bright spot is similar to what we obtained we saw from the previous diffraction pattern. However, as we can see here, there are different type of concentric rings are there. Okay, so these concentric rings, how they are getting formed? Let's say if we go back a little bit to the formation of the reciprocal lattice, like how we have conceptualized the reciprocal lattice. Let's say this is the Ewald sphere and this is the crystal. Incident beam is coming, and then let's say the reciprocal lattice is here. Okay, so this is the origin of the reciprocal lattice. Then we are saying that there are different types of reciprocal lattice will be here, right? Now if I am considering that this reciprocal lattice is of, let's say, 100, I am considering that this reciprocal lattice is 100. This, and another thing I told that when we rotate the crystal, that means when we rotate a single crystal, I am considering that this is a single crystal. So when I rotate the crystal, the Ewald sphere will be as it is. However, the reciprocal lattice will start rotating. Okay, so when the reciprocal lattice will start rotating, and how I have characterized this is 100, that point will be 100, because the distance is, this distance will be always d star 100, which is 1 by d 100, right? So the distance will be between this much. Let's say I am talking about this distance d star 100. Now what is happen? This is a single crystal. Now if I am considering a polycrystalline material, then what will happen in the polycrystalline material? The polycrystalline material, this is one direction. Another set of single crystal, they will be staying in another orientation. However, only when I rotate the crystal, the reciprocal lattice will rotate. However, the origin will always be on the circumference of this Ewald sphere. So what will happen in that case? In that case, let's say like this, all this. Okay, in that case my reciprocal lattice will also rotate. However, if my material is same, okay, then this d star distance will be always staying same. So this distance will still d star 100, and this point is corresponding to 100 plane. Same thing, if so, that means depending on the orientation of my crystal, what is happening? Depending on the orientation of my crystal, my reciprocal lattice is rotating. However, this, if I take another of my another of single crystal which is oriented in a different way, then what will happen in that case? That reciprocal lattice, origin of the reciprocal lattice will be staying here. However, my all the spots will be like this. Some will be coming as a and satisfying the Bragg's condition. However, if I am trying to figure out what is the nearest point from the origin, so this will be still 100. Now I can see that there is a pattern going on. What is the pattern? All the depending on the orientation, right? Depending on the orientation of the crystal, the 100 plane, let's say the 100 planes, they are changing their position. However, their distance from this origin, that is not changing. Why? Because the distance is dependent on the interplanar spacing. That means reciprocal lattice vector, which is inversely proportional to the interplanar spacing. So when I take in this case, what is happening? My center is staying as it is, and the distance where my planes are appearing, they are varying. The distance is not varying, however their positions are varying. So when this kind of structure happens, so what kind, so corresponding to this one, let's say this is my 0 0 0 of the reciprocal lattice. So the 0 0 0, that means the origin of the reciprocal lattice, all these planes, okay, all these planes will be which planes? So they will be considered as the family, they will be all these points, they are from the family of 100, right? So family of 100. So but the distance between them, whenever I calculate the distance, that distance they cannot escape. That means this distance that cannot go further. Why? Because this distance is always d naught 100. This distance is always fixed, because this is always fixed. So now I have, let's consider 20 of those single crystals staying in my sample. But in a polycrystalline sample, there are infinite number of single crystals, or the grains will be oriented. There are several number of grains which are oriented in different direction. So in that case, what will be the scenario? When there will be many grains which are oriented in different direction. But in that case, what will happen? This 100 plane will still be at that particular distance. In that case, those grains will always be staying so much close together that instead of a spot pattern, you will be getting a concentric ring. You will be getting a ring kind of pattern. The points will be staying so close to each other that you cannot distinguish, and eventually you will be getting a ring kind of structure. So since this is 100, the distance will be always d star 100. Now if I am talking about 200, then same thing will happen. 20, all the planes which are giving 200, they will be staying at a certain distance, and that distance will be d star 200, right? And if there are several number of grains of several number of grains, then what will happen? All those grains will stay at a distance of d star 200. However, you will see them as concentric circle. Same thing will be going on for other set of planes as well. Okay, and this is the reason why you are getting, so this is what a polycrystalline material, which we are getting it here. So polycrystalline material is nothing but a combination of several single crystal. Okay, several single crystals, it is a combination, and this beam which is coming in the center, that is called as the direct beam. Okay, and based on that, you can see this is 111 plane, this is 200 plane, this is 220 plane, 311 plane, and 222 plane. How we are able to index those plane? So this is the difference between a single crystal and the polycrystal. Here one interesting thing which I forgot to tell in the X-ray diffraction pattern, that so this is the ultimate diffraction, right? This kind of diffraction also, that means here we told that the diffraction will take place, and ultimately if a polycrystalline material is there, we should be able to get this kind of diffraction, right? But in our X-ray diffraction, we are not getting this kind of diffraction, because X-ray also is eventually means the phenomena is eventually diffraction, right? But here we are not able to get X-ray diffraction. We are not able to, and even if we are getting, we are putting a polycrystalline material, we are not getting this concentric rings. Rather, in X-ray diffraction, what we are getting? We are getting this kind of structure, right? One peak we are getting. This is I, this is 2 theta. So in X-ray diffraction we are getting. But does that mean we are doing something wrong? The answer is no. Why? Because in X-ray diffraction, it all depends on the detector that you want to use. So here in electron transmission electron microscopy, we are using an area detector. Okay, we are using an area detector. That means it is giving information all in x direction as well as in y direction. In both direction it is giving us information. In X-ray diffraction, what do? We put a 1D detector or a line detector. That means, let's say I am just magnifying the image for you to understand. So we are putting a line detector like this. We do not put a detector which covers the entire of this concentric rings. Rather, we put a detector like this. So when we put a detector like this, we count how much intense the peaks are. How much intense. So here you can see this, the closest to, that means the 111 plane, it is having much higher intensity. So we only calculate based on the distance from the center. We can calculate the 2 theta, or we can calculate the d spacing. Okay, so 2 theta we can calculate, and from there based on the intensity, so 111 here it is much higher in intensity, right? When we are going to collect all the intensity. Then next comes 200. 200 is this one, so it is a little bit lower. 111 is very much higher. Then comes 220, right? So collecting all the intensity, we are converting those photons that we are getting it here, we are collecting. Then what we do, since 111 is giving highest intensity, so we are putting like this 111, and then comes 220 like this, then 222 like this. So based on the position of 2 theta or d, we are getting intensity. So in X-ray diffraction we are putting an 1D detector. That is why we are getting this kind of output. And if in also in X-ray diffraction, if you are going to put an area detector, you will be able to get this kind of diffraction, because this is the ultimate diffraction pattern for a polycrystalline material, right? So yes, so this is one. Now coming to the down image, the below image, what is this? This looks like a polycrystalline materials diffraction pattern, but it is not concentric rings. Rather, it is concentric rings. Rather, it is bright at some position or dark in other position. So what does it mean? Does it mean it is single crystal? No. Why? Because I can see that there are concentric rings are there. That means it is polycrystalline. However, only at this orientation, between this orientation and this orientation, the lights are, or the diffraction spots are extremely high. That means in a particular orientation, if my diffraction spots are extremely high, my grains are oriented in that direction. That is what I call it as preferred orientation. And what do I mean by preferred orientation? What is the definition of preferred orientation? Preferred orientation means my sample is having texture. Okay, so these are the three different types of samples or the diffraction pattern which we always see when we put our sample in a TEM chamber. So now we will go through that diffraction using small probe. So in a conventional diffraction pattern, in a conventional transmission electron microscope, so when we always try to get the diffraction pattern, electron diffraction, so in that case our beams are always almost parallel, electron beam. Why it is almost parallel, we will derive it now. And the specimen and the resulting diffraction pattern from a periodic sample consists of a array of sharp spots in the back focal plane of the objective lens. Okay, so these are the different thing that we have to consider. So why we are saying that they are almost approximately parallel on the incident specimen? Because as from my perspective, if I am seeing that this is the specimen and this is my electron beam, right? This is my incident electron beam and this is my specimen. Then why I am saying that it should be normal, right? Then why I am saying that this is parallel? So it is parallel in the sense that, let's say, so we know that diffraction can occur only when n lambda is equal to 2d sine theta, right? So n lambda is equal to 2d sine theta. If I am taking an example of copper now, let's say my material is copper, for 111 plane if I am talking about, then the d spacing is somewhat close to 0.21 nanometer. Okay, for copper 111 plane, right? the d spacing is this much. So for copper you can search the lattice parameter A. Since it's an FCC, you can search the lattice parameter, and from lattice parameter you can put you can get the value of d spacing, right? Since I have the HKL and the d spacing, so what I will do, let's say I'm assuming that lambda is around 3.35 picometer, right? I'm assuming this is the lambda means the wavelength of electron, right? If I get all this if I put all this information in my diffraction, since my diffraction is taking place, so n lambda electron is equal to 2d sine theta. Let's say theta is theta b. I am putting n, I'm first order considering first order diffraction. Lambda e is equal to 3.35 picometer. Picometer means how much? 10 to the power minus 12. Okay, so 2 into d I am getting 0.21 nanometer into sine theta b. If you solve this equation, you will get theta b as close to theta b, you will get close value of 0.46 degree. Okay, you are getting theta b as 0.46 degree. So it is that small. How small? That means, let's say I am saying that the diffracted plane is taking place. Let's say I am considering as I'm giving you a comparison between X-ray diffraction and electron diffraction, transmission electron diffraction. In X-ray diffraction, we always thought that since our atom is our incident beam is coming and going like that, we always thought that the planes are situated like this. Why we thought like that? Because we were the theta value, right? The theta value was varying between it is approximately large angle. Let's say it is for now, if I put the same thing, it will be somewhere close to 25 degree, the theta value. That means my incident beam theta is nothing but the incident angle between the incident beam and my plane. So my theta will be somewhat close to 25 degrees. So in that case, I was able to imagine my planes are like this. Incident beam is theta is 25, similarly reflecting is 25. Now that I have got my Bragg angle as 0.46, can you imagine where I will be? That means if I am putting my sample like this, and if I am saying that these are my planes, I will not be anymore saying that my beam is coming like this, my beam is going like this. Rather, my beam will be coming at an angle of 0.46 degree. 0.46 degree is less than 1 degree. So my beams will always be going like this. So my plane is, this is my incident beam and theta b is this much, and this is my reflected beam. So the for a transmission electron microscopy, if I want to, and here this is the schematics as per my X-ray diffraction. However, in transmission electron diffraction, the beam is always coming from top. So for electron diffraction to take place, my sample or the Bragg's plane has to be almost parallel to the incoming incident beam. Then only it will come like this and it will go. So it will be 0.46 means, still I am exaggerating this image. 0.46 means it is almost coming. Let's say this is the plane, it will come, just touch it and then go. So that much difference is there. So for electron diffraction to happen in a transmission electron microscopy, the plane from which you want to get the Bragg's, you want to satisfy the Bragg's condition, that plane has to stay parallel to the electron beam. So this is what I meant by, in conventional selected area diffraction, an approximately parallel electron beam comes, and the information that we are always getting, the planes are not situated like this one. Rather, the planes are situated like this. So we'll be getting information from this kind of structure. Okay, and earlier we saw that how the diffraction can happen, like parallel. If we are making the beams parallel, then we will be getting all this selected area diffraction. However, in recent times, so if we saw that if we can make the beam completely convergent, then what will happen? Then the diffraction pattern that we are going we got, those patterns actually got a little bit bigger. So this kind of since we are using the diffraction, we are getting the diffraction pattern using instead of parallel beam, using a convergent beam. So this kind of operation we use it in convergent beam electron diffraction, or CBED. Okay, so it is called as convergent this is convergent beam electron diffraction. And the principle behind this convergence, the mechanism, how do you obtain this? By changing the C2 lens and the strength of C2 lens, that means the condenser lens and the upper objective lens. I told in the last class that there will be a lens system called CO lens system, condenser objective lens system. So changing the strength of those lens, we are able to focus our sample onto the focus our incident beam onto the sample, and since we are converging all those beams, then only this electron diffraction pattern is known as convergent beam electron diffraction. Okay, so here one of the striking feature that we are able to see, that earlier in the normal diffraction pattern, the spots are one bright spot would be there and small bright spot will be there, and surrounding that there would be many bright spot would be associated with it. However, here you can see inside of the bits, you can see a magnification. So this CBED, you can say a magnified version of a CBED, you can say a magnified version of the SAED. Why? Because SAED you may collect from this might be the sample, and SAED you may collect from this area. Okay, so though the selected area is still small as compared to the sample, but still it is quite large when you are talking when you are comparing SAED with your CBED, that means convergent beam electron diffraction. So as CBED, you can see what is happening, what are there in the central bright spot or the bright spot, and here you can see all the spots and the Kikuchi lines. You can see there are many lines going through them, and those lines are called as Kikuchi lines that we studied in ACM. Okay, so all these things now you can see it in magnified version. However, you could not see all these things here. If this is the diffraction selected area electron diffraction, you could not see it there. However, if you go for CBD, convergent beam electron diffraction, you are able to see those spots. So, and how we are able to means there are different types of operations also associated with CBED, and one of the type like when I say that we have to converge the beam, then you can ask questions like how converge we can do. Shall we if we are converging the beam and we are getting more information, that means shall we go for a large convergence angle? Let's say I am now talking the total convergence angle is 2 alpha. So shall we go for an extremely high convergence angle, so that we will be getting more will be able to get more information from our diffraction pattern? But the answer is no. Why we can't do that? So since here look at three different scenarios, A, B and C. Here you can see small 2 alpha, that means total convergence angle when we are talking about, and all the specimen are thin specimen, right? So when we are talking about that, so no doubt we will get the diffraction pattern here. In this case, no doubt we will get the diffraction pattern larger than, or the magnified version of a selected area diffraction pattern, but there still will be some kind of some kind of filtering, or I would say some kind of more resolve we could have done, right, when the angle is small. Then what we do, let's say the angle is a little bit medium, right? Medium means not too small, not too large. Then you can see all these spots which are, you can see in case in the diffraction pattern 1, they are magnified, and you are now able to see a much more distinct diffraction pattern, distinct feature in that diffraction pattern. What are the Kikuchi lines are there, it is clearly visible, and inside the bright spot what is there you can see. So you are able to see. And here if you take the large convergence angle, in this case what will happen? In the large convergence angle, you are getting an extremely broad or extremely wide the central bright spot, but you are not able to distinguish anything, right? So when you are getting this kind of spot, this is known as co-cell pattern. Okay, co-cell pattern is the pattern in the CBED when you get when there will be all overlapping cones will be there, because remember from the diffraction, if you remember from the lowest diffraction condition, then the cones which are getting diffracted or getting scattered, they are called as cones are called as co-cell cones. Okay, and those cones will be eventually cut by a screen, and that is how we are getting a ring kind of structure. So since these cones since these cones are in 3 dimension, so all the 3 cones are overlapping with each other, all the 3 cones in this scenario. Okay, and this is what called as co-cell pattern. And when all the 3 cones that are getting formed in this scenario are not overlapping with each other, that means distinctly they are placed distinctly at a far away from each other, that pattern is known as co-cell-Molenstead pattern. Okay, and in the co-cell-Molenstead pattern, there is a subset, we can say that it is neither overlapping extreme completely, all the 3 cones are not overlapping with each other, neither they are completely distant from each other. That means only a small part of a cone is overlapping with the other cone. So in that case, that is also known as this co-cell-Molenstead pattern, and that is the optimum case that we can go at CBD, that means convergent beam electron diffraction, to get this structure. So there is no hard and fast rule for the medium, that means the 2 alpha value based on the material where when you put it in TM, and accordingly we go and see what is the optimum 2 alpha that we can go, and we can get this electron diffraction pattern, and we can see those features completely, right? And so now coming to another thing, that another terminology associated with electron diffraction is known as camera length. So camera length is not a real length, but rather it is a projected length. So the length from the specimen to the diffraction spots, that means these are the diffraction spots are in the screen. So here the screen is there, on top of which the diffraction spots are getting formed. So it's a projected length. And what is the role of this camera length? Generally this camera length is denoted as capital L. What is the role of this camera length? The role of this camera length is to relate the distance of a spot. That means this is an undeviated spot, right? Because this is an incident beam. If it is coming, this is the direct beam, so this is an undeviated spot, or I can say that the direct beam is coming, okay, and falling it here. However, here this after the diffraction, let's say this is theta b angle, and this is also theta b angle. So after the diffraction happens, so this is a diffraction, this is a diffracted spot. So the role of camera length is nothing but to relate the distance between origin of the diffraction pattern to the d-spacing of the set of planes from which it comes. How it does, we will see. Let's say this is the diffracted spot, or the origin of the reciprocal lattice. Let's say this is a diffracted spot, and between those I am taking any distance as r. Okay, reciprocal. Okay, so I am taking any distance between them as r. So how does it relate? Here I have told that this is capital L, camera length, and this is the 2 theta. 2 theta means I am taking 2 theta as my Bragg's angle. Okay, so now if I am taking 2 theta as my scattering angle, then what will happen? 2 theta is my total scattering angle. That means my if I am considering the Bragg angle will be theta b. So that is why 2 theta, because so this is theta, this is theta, this is also theta. So this total angle is 2 theta. That means my beam is coming at an angle of theta only. Okay, so if I take the geometry of this triangle, let's say A, B and C, in triangle ABC, if I am talking in triangle ABC, this is a perpendicular. So if I start putting tan theta, let's say tan 2 theta will be how much? BC by AB, right? This tan 2 theta will be BC by AB, P by B. So BC by AB will be how much? BC will be R, AB will be R, L, right? So this R by L tan 2 theta. Now I know that this 2 theta value is extremely small, because we saw it in previous slides that the angle that we are talking about when diffraction is taking place is less than 1 degree. So that is, so in that case I can write tan 2 theta will be somewhat close to 2 theta. So I can put it as 2 theta, right? This tan 2 theta I am putting it as 2 theta. Now if I am doing that, and also I know that for this condition to take place, my diffraction, the diffraction phenomena n lambda is equal to 2d sin theta. That one I can put, right? This is the diffraction condition. So this is from geometry, this is from diffraction condition. So now if I am talking about the first order reflection, lambda is equal to 2d. Similarly I can write sin theta will be theta. I can write that. So 2d theta I can write. Now you can see, if I am talking about 2 theta, from here I can write 2 theta will be lambda by d, right? So this is equation number 1, this is equation number 2. If I equate the equation number 1 and equation number 2, what will be happening? R by L is equal to lambda by d, right? And here this expression is giving me Rd is equal to lambda L. Okay, remember this expression. This is one of the most important expression in transmission electron microscopy, because using this expression only we will be indexing all the diffraction spots. Okay, Rd is equal to lambda L. And here what is the value of R? R is nothing, the distance of the diffracted spot from the origin, and d is what do I mean by d? D is coming from n lambda is equal to 2d sin theta. That means d is interplanar spacing. And what is this lambda? Lambda is the wavelength of this incident beam, and L is the camera length, and L is the camera length. Here total expression of lambda L is known as camera constant, and this value is constant for your transmission electron microscope. So that means if I have to calculate the value of R, okay, so if I have to calculate the value of R, then I know that Rd for my transmission electron microscope where I am putting, okay, that length will be always constant. The operator will always give you the value of camera constant, it will be given. So once I know that this constant, so this constant value I know, then I have to calculate the distance. I know the distance also, this d, right? This d is associated with my material. Now I can calculate how what is the distance that my material, my diffraction spots will be going to be formed in my diffraction pattern, right? So this is, always remember, Rd is equal to lambda L, and what each notation signifies. Okay, and this diffraction pattern always we get it in reciprocal space, right? And the reciprocal, in the reciprocal space there is a definite relationship between periodicity and orientation of the object with spacing and orientation of the spots, right? So in the reciprocal, as Lavey did his first experiment in a transmission mode, taking zinc blende material. So he observed that the diffraction, the diffraction spot, the diffracted spots always change their position according to the orientation of the crystal, right? So reciprocal space is nothing but a set of wave vectors for which plane wave will be having periodicity of lattice. Why I am saying it as wave vectors? Because if I am talking about in reciprocal space, then I can always represent my electron beam as a e to the power I 2 pi k into r, right? My electron wave vector I can talk, I can speak this, let's say psi is my electron wave vector. I can I am putting it in this form because I can get electromagnetic, I can represent in this way, I can represent my beam at the electromagnetic wave which is having periodic saturation. That means in at an interval, at a particular interval, this wave will be having periodicity. Okay, so that is why this in set of wave vectors for which the plane wave will have periodicity of the lattice. My lattice will be having periodicity and this wave vector will be representing. Okay, and coming to the reciprocal space, so this is a specimen and you can see, so this is the r is the distance of the spot from your direct beam or the direct the undeviated spot. So here you can see the thing that I was saying, that 0.46 degree, you can see the planes are oriented in this direction. All these gray color lines which are oriented in this direction, and this is the incident beam, and once it gets deviated, it is getting in the film, it is creating a spot like structure. So similarly, this is one directional, right? Or this is the planes are coming, the planes are in this direction, like in the planes are oriented the planes are going into the screen and coming out of the screen. So planes are oriented in that manner. Now if I put two more another plane, then what will happen? The plane, so this is plane 2, right? This is plane 2, and the beam will come and it will be diffracted beam will be getting diffracted from plane 2 in this manner, right? And when I am taking another beam, that beam will come and it is going to, so now this ray is coming out of the plane, out of the slide, as you want, if you want to visualize. Okay, so this is how I am getting the diffraction pattern of 2 here, 1 here. Okay, so this is how, if I am having a multiple number of planes, then how the diffraction pattern are going to get formed, we can visualize from this diagram. Okay, and then how do we know that there are multiple reciprocal in the reciprocal space, there are multiple diffraction pattern will be there, but how do we know that the angles between them, how do we know like the relationship between them, what is the orientation relationship between them, what is the distance between them? That we do using stereographic projection. So what do you mean by stereographic projection? It is the projection of points from the surface of sphere onto the equatorial plane. Imagine a crystal like this inside this thing. Okay, first you imagine a crystal like this. So when you imagine a crystal like this, and what you do, so all these faces you can see, one where this is a square faces, one where this is having 1 2 3 4 1 2 3 4 5 6 7 8. So this is having an 8 spaces, let's say this is having 8 sides, this is having 4 sides, so all these, and this is having 6 sides, right? So imagine a crystal where you are having imagine a crystal like this, and here you draw a normal through all of these faces. That means from these 4 side face there will be a normal coming, from this 8 side faces there will be a normal coming out towards you, from this 6 side from the 6 side face there will be a normal going coming out towards you, but in an inclined direction towards your right side. Okay, similarly there will be a normal coming out from this side also towards you, but in your to your left side. So imagine all of those normals coming out, and imagine that this crystal is situated inside a sphere. Okay, so once you see that, imagine that this crystal is inside a sphere, and somewhere these normals which you are drawing out of these faces, they will be interacting or they will be intersecting the surface of the sphere. Let's say those points are these ones. Okay, now what is the role of so how do we define the stereographic projection? So these points, this is a 3-dimensional, right? So when I'm saying that you imagine all the angles, so you imagine this crystal, that means you are imagining a 3-dimensional crystal. So when you want to put it all these 3-dimensional crystal into a 2-dimensional drawing, what you do? This is the equatorial angle. Sorry, not angle, this is the equatorial plane. Okay, and this equatorial plane is actually lying on the great circle. So great circle is this one, it's a primitive great circle, it is called in stereographic projection. So this is lying on great circle, a primitive great circle. So this equatorial plane you put, now you have taken all the normals and you got them intersected with the surface of this sphere. Now from those points you just draw a projection onto this point, onto this plane. This, let's say one of the normals is coming and interacting with this and then going out, right, of this plane. Then what you do, you put them, you try to put them or project them onto the equatorial plane which is lying on the great circle, and that projection is entirely known as this stereographic projection. Okay, so it is nothing but an drawing, the two-dimensional drawing of all the three-dimensional angles. And when this projection you are seeing that there is a lot of points are there, all these center is there. So how do you see the stereographic projection? You see the stereographic projection, let me draw. So okay, so you see the stereographic projection. So all the points now are drawn on this circle, right, or circle, or the circumference of this circle. So from which angle you are seeing? You are seeing from this angle, or I can say, okay, I am drawing it from top. Okay, so this is the eye. So you are seeing it from the top of the thing. That is why the point 0, 0, 1, let's say this is the point of 0, 0, 1, the fully straight, you are seeing it here, point of 0, 0, 1. So the 0, 0, 1 normal will be only seen, that means you are only seeing the top end of the 0, 0, 1 point. Okay, so that is what it is called as, that means 0, 0, 1, this is the zone axis of the 0, 0, 1. Okay, and if you see, so there are the pole, this point, center point. So if you see, that defines the on which zone axis you are going to view the view your diffraction pattern. So since here this is the 0, 0, 1, this is called as 0, 0, 1 stereographic projection. Here you just, if you you rotate the crystal in such a way that you rotate the crystal, and then what will happen, all the points, right, all the points, because once you rotate the crystal, the reciprocal lattice will be also rotating, so all the points are also going to rotate. But and you have rotated in such a way that now 0, 0, 1 from here it has shifted to here, and now 0, 1, 1 which was earlier here, it is coming to the center one. Now it is a 0, 1, 1 projection, stereographic projection. Similarly, if you want to rotate in some other directions also, it is 1, 1, 1 stereographic projection. Okay, so these, the points which are staying on the center at the center of the stereographic projection, those points are known as the zone axis. Zone axis is nothing but along the direction along which your electron beam will be incident on your specimen. Okay, and that brings us to our Weiss-Jones law. Weiss-Jones law is so Weiss-Jones law tells us that along which directions it's not like you can you know all the planes, and you will be able to see all the planes, and any random direction if your electron beam is coming, then it will be interacting with getting diffracted from your material. No, if I am telling that UVW, so UVW is the direction this is the direction of the electron beam. Okay, UVW is nothing, the direction of the electron beam. Okay, and if I am saying that for me to view all these things, like I want to view this set of plane, it is not like always necessary that whatever set of plane I get from this transmission electron micrograph is sufficient for me. Let's say here 100 you are seeing, 110 you are seeing, I want to view a particular plane, and according to that plane I want to check. Then what do I do? Let's say that particular plane is, I am saying, HKL. So in that case, if I want to view the HKL plane and my zone axis is UVW, then according to Weiss-Jones law, the formula is HU plus, excuse me, then according to the Weiss-Jones law, HU plus KV plus LW should be equal to 0. Then only if, let's say, you want to see a particular plane which is 1 to 1, let's say I want to or my diffraction is currently giving me 0 0 1 plane, 1 1 0 plane, 1 1 1 plane, but there is no mention of 1 to 1, but I want to see this 1 to 1 plane. Then what will I do? I will put this 1 to 1 in such a position that I will tilt my sample in such a position that this 1 to 1 is visible. And how can I do that? By observing this Weiss-zone's law, HU plus KV plus LW is equal to 0. And here I am saying the zone axis means the direction along which the direction along which the electron beam is coming. It might be parallel or it might be anti-parallel. And here I can say that how you can say that HKL and UVW, like physically how you can say that HKL and UVW, the multiplication HU plus KV plus LW will be 0. Let's say all the planes, if you want to see, let's say my electron beam is coming like this in UVW, right? So my electron beam direction is like this and my plane is parallel to it. And but we know that if I am talking about HKL plane, then the direction normal to this HKL plane will be also HKL direction. If you want to visualize, you can take like it is like this. Okay, let's say I'm talking about HKL. Let's say I'm talking, this is X, this is Y, this is Z. So I'm talking about 0 0 1 plane. Which one is the 0 0 1 plane? 0 0 1 plane is this one, right? If I'm talking about the 0 0 1 plane, so I will write 0 0 1 plane. But the direction 0 0 1, if anyone can find for me, the direction is also along this one. That means my plane is, if I want to write my plane, then I can write my plane in terms of not only in plane but also I can write 0 0 1 direction. So eventually 0 0 in a orthogonal or cubic system, my 0 0 1 plane eventually will give me the 0 0 the 0 0 1 direction will eventually give me the normal to the 0 0 1 plane. So if now I am saying that this is UVW and my plane is now HKL. So if my plane is HKL, then the normal to this HKL plane will be along this direction, right? So normal to this plane will be along this direction. If the normal will be HKL direction, so this is the direction UVW. So I can do, let's say, HI plus KJ plus LK. I can do that. And now since this is dot UI plus VJ plus WK, I can do that. So now since these are all perpendicular to each other because it is almost parallel, so now these two are almost perpendicular to each other, so the multiplication of this will be 0, which will give me HU plus KV plus LW is equal to 0. So now you can visualize how you are able to see the Weiss-zone's law, how you can physically able to visualize. Okay, this is the condition that we use to go to a particular plane. And using this Weiss-zone's law condition and also stereographic projection, we have derived that these are some of the standard diffraction pattern. And how we derive those standard diffraction pattern? First two diffraction pattern is for BCC, next two diffraction pattern is for FCC, the next one are for HCP. So here you can see, so there are different kind of, so here you can see an written like B is 0 0 1, that means your zone axis is 0 0 1, that means your electron, the direction of incident beam electron is 0 0 1. However, here you can see that there is one axis, one spot is there, then you can see a hexagonal kind of structure, but this structure is not same as of this structure when you are coming to this structure. Why? Because the zone axis is changed. Now the zone axis since now is changed, HU plus KV plus LW is equal to 0. Those planes might not be, all those planes which are here earlier, they might not be they might not be able to satisfy that Weiss-zone law. So now if you are changing your zone axis, then all those planes which are satisfying the Weiss-zone law, those diffraction spot or those planes will only appear in the diffraction spot. Okay, and how so these are called the diffraction pattern, and how we are going to these are the standard diffraction pattern. You need not to remember everything, but if you can means one or two there is a pattern actually. If you can observe those pattern, then it will be helpful for you, because question might come in the examination that derive electron diffraction pattern when the zone axis is 001 or 011. So you can easily write. So how to now let's say how to now index one diffraction pattern. I will just go it in little bit. So let's say my diffraction pattern is like this. I am getting some diffraction pattern. Okay, I don't know anything. Only this diffraction pattern has been given to me. So what I will do, let's say this, I know that means this one is my bright spot. That only the diffraction pattern has been given. This one is my bright spot, and the distance to two different points are given. This is my bright spot, right? From here, let's say I am considering it is R1. R1 means the distance. If you remember, R is the distance here, this distance, that means the distance from undeviated spot or the direct spot from the any of the diffracted spot, right? So here also I am taking this is R1, and this is I am taking it as R2. I don't know what this spot belongs to, what this spot belongs to. So initially I'll just take an assumption that this is R1, this is R2. Now if you remember that formula I told, RD is equal to lambda L, right? So similarly I can write R1 D1 is equal to lambda L, R2 D2 will be equal to lambda L. Why I am writing lambda L? Because it is a camera constant, and for one transmission electron microscope, camera constant will be always equal. So from these two, if I write combinedly, R1 D1 will be equal to R2 D2, right? So if I can write now, R1 by R2 will be equal to D2 by D1. What do we mean by D? D is the interplanar spacing. D1 is the interplanar spacing corresponding to this spot. D2 is the interplanar spacing corresponding to this spot. Now I don't have D1 and D2 value. So how should I know? Let's say I am putting this point as 0, 0, 0 as my origin. So D1 and D2, if the information will be given to you in the exam that this is an FCC material, this is an BCC material. Let's say I am assuming that this material is cubic. So then what I can do? 1 by D square will be equal to, what is the value of 1 by D square? I can write 1 by D square is equal to, this is okay, D2 it became this is okay. So I can write 1 by D square will be equal to H square plus K square plus L square divided by A square. This one I can write in cubic system. Then D will be equal to A divided by H square plus K square plus L square under root, right? So D1 I can write, D1 will be A divided by H1 square plus K1 square plus L1 square. Why I am not writing A1? Because it is a one material, and in one material the lattice parameter will be always same. HKL however corresponds to the plane of the system. So that is a different plane but same lattice parameter. So D2 will also be A divided by H2 square plus K2 square plus L2 square. Now if I put D1 value, D2 value in this equation, what I will get? I will get R1 by R2. Since D1 and H1 they are inverse, H1 square plus K1 square plus L1 square, they are inversely proportional. Then what I will get? R1 value is equal to, this is H1 square plus K1 square plus L1 square divided by H2 square plus K2 square plus L2 square. This value I will get. Now if I do not have any other information, only I have information whether this is a cubic structure, then what I will do? I will have to consider two set of H1 K1 L1 and H2 K2 L2 in such a way that this value R1 by R2 gets satisfied. So what do I mean by I have to consider these two? Let's say R1 by R2 value, I am getting it as root 2. For now, let's say consider this R1 by R2 value, I am getting root 2, right? So this root 2 I can write R1 by R2 is equal to root 2. How I can write? I can write it as 1 square plus 1 square plus 0 square divided by 1 square plus 0 square plus 0 square root of 1, right? This is root 2, this is 1. I can write this one. Now if I compare this equation with this equation, I am getting like H1, K1, L1 corresponding are they are not in no bracket, so they belong to 1 1 0, okay, and H2, K2, L2 they belong to 1 0 0, right? I can write this one. That means the point corresponding to 1 in this the spot corresponding to one spot, that will be 1 1 0. The point corresponding to two spot, that will be 1 0 0, right? Since this is 0 0 1, if this is 1 1 0, then I can write easily this point as 1 bar 1 bar 0, right? So this is how I do the indexing, but there is a catch here. What is the catch? I cannot put 1 1 0. Why? What is the problem now? If I am saying that this 1 1 0 and 1 0 0 I can put, I am getting the ratio of root 2, right? But the problem is, even if I consider it is as BCC, let's say I am considering it as FCC, then what the in FCC here the selection rule will come into play. So if you are selecting that your material is FCC, that means HKL should be unindexed. Here in 110 HKL is not unindexed, unmixed. The Miller indices of your plane will be unmixed. So but here 110, 1 is odd, 1 is odd, 0 is even. So it is a mixture of your indices. That means 110 is a forbidden reflection. It cannot come in forbidden reflection 110 or 100. So either you will have in FCC, let's say you will have 111, you will have 220, you will have 200, you will have 020. All these spots you will be getting. You should not get 100, 110 if you are considering it as FCC. Even you can say that I am considering it as BCC. Okay, in BCC H1, K1, L1 you will get as 110. Why? In BCC the condition is H plus K plus L should be even number, right? But here in this case 1 plus 0 is an odd number which is not divided by 2. So in BCC you will not be able to get this number. If I am considering this for now, let's take an example that I am considering that this still R1 by R2 is equal to root 2. This expression is valid. But how? But what if I consider now that R1 by R2 is equal to 2 square plus 2 square plus 0 square divided by 2 square plus 0 square plus 0 square. Is it now possible? I am getting H1, K1, L1 is 220. I am getting H2, K2, L2 is 200. Right? Is it still possible? All are odd, all are even, and I will still get the ratio of root 2. That means my first point, whichever I was considering as 220, now this is 110, now this has become 220, and this point which was I was considering 100, this point is actually 200. Then you can ask that if you are talking directly on 200 and 220, then where these 220 are there? 220 is somewhere here, and this diffraction pattern which are not coming, we put an X here. If you see somewhere we are putting all this diffraction pattern, however we are putting X. That means X means these are the forbidden reflection in that zone axis. Okay, so this is how we index a diffraction pattern, by considering selection rule and by putting the formula RD is equal to lambda L. So this is how you have to select a diffraction pattern, and after that you have to calculate the zone axis also. The zone axis, how do you calculate? Whether these pattern actually come on your for your diffraction pattern or not. This is the HKL, and you have to calculate the zone axis. That means zone axis is given by U, V, W. So you have to calculate the zone axis, and the zone axis, how you can calculate? Okay, I'll write somewhere here. I am writing the zone axis. You can calculate it as so A, B, C, H1, K1, L1, H2, K2, L2. Why I am putting this thing? Because this zone axis will be consisting, this zone axis is nothing but the line where two planes are, this zone axis is considering all the information from two planes, and when two planes get intersected, what will be the result? The result is a line, like we saw it here. Okay, when two planes are getting intersected, the result is a line. Okay, so this line, since two planes are getting intersected, how we will able to derive the zone axis? So ABC, and this this ABC is the three axes, like IJK you can say. So that means you will be getting K1L2 minus K2L1, V you will be getting H1L2 minus H2L1, W you will be getting H1K2 minus H2K1. So you have to calculate all these things if you are to give an indexing of diffraction pattern. Okay, now coming to the Ewald sphere. So far whatever we have talked about, so this is where the electron beam is coming and the reciprocal lattice are there, and you can see these are all these. So this is an undeviated beam, and so here earlier whichever I was talking about in X-ray diffraction, we are talking about Q is the scattering vector. From now onwards I will tell the scattering vector as, so in electron diffraction we talk about the scattering vector as G vector. Okay, so here this is the undeviated beam, and after the diffraction from this point, you can see this is the reflected beam diffraction, and this is the Ewald sphere. So when, and this G, so since this is 1 by lambda, this is the center, so this distance is also 1 by lambda, and this G which connects the which is the difference between the diffracted beam and incident beam, so this G is given by, so I have so yeah, so this is the zoomed version of this phenomena that is taking place. So here you can see from the vector diagram, G will be equal to K minus K naught. Okay, and you can say that in the diagram, in this diagram, if you want to calculate, this is 2 theta, right? 2 theta is the angle, the scattering angle, and this will be theta from the geometry. So if you put an equation, if you want to calculate the Bragg's angle, you will be able to Bragg's diffraction law, you will be able to put the geometry to this sphere and to entire, let's say, X, OP and QOP. These three, if you take the triangle, the geometrical relation between Q, O and P, and then compare it with the relation coming from the triangle X, O and P, then you will be able to derive Bragg's law, n lambda is equal to 2d sin theta. Okay, so same thing I have done it here. So far so this is a magnified version of what is happening here. So far whatever we have talked about that our and when the diffraction takes place, when the reciprocal lattice points will be on the surface of the Ewald sphere. So this reflecting sphere is nothing but the Ewald sphere. However, we are always talking about in perfect scenario, right? And we are saying that all the time the diffractions that are taking place, those points, those reciprocal lattice points are always staying on the surface of the Ewald sphere. And our incident beam is always parallel, but in real life that is not the case. Why? Because though we are considering that the Ewald sphere surface only when the diffraction takes place, the reciprocal lattice point are staying on the surface of the Ewald sphere, the diffraction takes place, but there will be some amount of deviation associated with it. Okay, and those the probability, though the diffraction is weak, in this case you can see this is a perfect staying on the surface of the Ewald sphere, no matter how big the Ewald sphere is. One Ewald sphere radius is 1 by lambda. We are considering 1 by lambda means 1 by 10 to the power minus 12 meter. That means the radius is 10 to the power 12 meter Ewald sphere, right? Why 10 to the minus 12 meter? Because the wavelength of the electron is in picometer. So the radius of the Ewald sphere is 10 to the power 12 meter. You can imagine how big that sphere is. It will be more or less. You can, if you know, if you know the radius of the Earth, it's to that comparison you can do. So this is the radius of the Ewald sphere. Still, all the reciprocal lattice point will not be staying on top of that, and even if they are not staying on top of that, we will be getting some amount of diffraction. That diffraction might not be completely we are getting intensity. Why? Because the intensity versus 2 theta, the Bragg's angle, when we consider, it will always follow a distribution like structure. It will not be somewhat like this and then 0, then this, then 0. So it will always follow some kind of distribution structure, distribution thing. So that is why even if these points are not exactly staying on the surface of the Ewald sphere, they still contribute to the diffraction. And when they are not staying exactly on the Ewald sphere, there will be always some amount of error associated with it, which is called as S, excitation error, or this S is called as deviation parameter. Okay, and this error, you can see this is the Ewald sphere, and whatever error this thing, so be it this beam or this beam. So now the K is this one, KD is this one. So if I consider the G vector now, what will be? So if I consider the G vector now, so now I can write KD minus K will be equal to, so if my KD is ending at this point and my G vector is ending this point, and then I have to add another point. So G vector this point, and then S vector in this point plus S. So this is how I will be able to now write my all of expression. That entire diffraction is not an ideal scenario, and that parameter that which is not ideal, which is the deviation scenario where it is happening, that parameter is called as deviation parameter. So always remember K D minus K, that means K diffraction minus K will be always equal to G plus S. S is nothing but the it is some amount of deviation. Okay, and this deviation is generally okay, this one. And this excitation error is a measure of how far we deviate from the exact Bragg condition, which is we saw, and we defined whether S is positive or negative. When the S is negative, that means the G, that means this point, when this is outside the sphere, it is always negative. When the G is inside the sphere, let's say my point is, in earlier cases, here everything is inside the sphere. We'll see in a few moments that how, let's say my G is inside the sphere. Okay, so then in that case S will be, that means my deviation parameter will be it will be more. And to cover that, to also, so now what we did, we told that this, even our sample is not staying in the perfect Ewald sphere, still some amount of diffraction we will be considering. So to attach to know that still that but the Bragg's condition, we cannot say that the Bragg's condition is not satisfied. So instead of points, what we did, now considering instead of points, what we did, we consider as an elongated object. So now if we are considering, instead of a point, this point, we are considering it's an elongated object, we can say that Ewald sphere is going this, and then still my elongated object is touching the Ewald sphere. That is why, though the some part of that means the Ewald sphere is not completely intersecting my elongated object, but still I am getting weak diffraction. And this elongated object is now earlier we are considering reciprocal lattice point. Now we are considering reciprocal lattice rods, or known as railrods. So why the railrods came? Because of the deviation parameter that is coming due to this when we deviate from the exact Bragg angle. And this deviation parameter and this S, reciprocal lattice rods, is this deviation parameter gives us how thick our sample is. So this S will be dependent on 1 by T. Okay, so S is equal to 1 by T. So it is dependent on the thickness of our sample, and the thickness is related to this rail rods. Okay, the reciprocal lattice points we are earlier considering, that is the kinematic theory. Now we are considering the more practical aspect of our diffraction, that is called reciprocal lattice rods. And now you can see there are different types of when I talked about the diffraction pattern. Here you can see the only the receiver, the evolved sphere will be a sphere, the circumference will be spherical thing. So the G, that this G point is nothing but the reciprocal lattice, the point at which the reciprocal lattice vector which is situated at a distance of reciprocal lattice vector. But similarly there will be also another set of vectors which will be associated from the origin, and those points will be also contributing to the diffraction. So the first, only when we are talking about G, that means the point which is situated only in at a distance of G, that means at a distance of reciprocal lattice vector from the origin, those things are called as, all those points will be consisting of ZOLJ, that means zero order Lave zone. And all the other points which are also staying on the surface of the evolved sphere, however we were not able to see it in conventional TM, those will be consisting your HOLJ, that is higher order Lave zone. Okay, so whatever we see in a conventional SAED, right? So whatever we see in a conventional SAED, we see all diffraction from ZOLJ, zero order Lave zone. That means all the information that we get, whichever I was showing in previous slide, that you have to index these peaks. So all those peaks we will be seeing inside this one. Okay, all the other peaks, so this is called the ZOLJ, and all of these peaks, they are called as HOLJ. That means the first order Lave zone. FOLJ, you can see that is first order Lave zone. SOLJ, second order Lave zone. For those Lave zone, what will be the criteria? The criteria will be, we can see that later when we see it in vector notation, we can see how the K into R, that the multiplication of the K into R, how it will be giving you some integral value. So when we'll see it in the next class. So whatever in electron diffraction we are getting from SAED, this will all be considered inside this one, that means zero order Lave zone. Okay, so diffraction from the small volume, same things what I was saying, that if the S, the Z is nothing, so how the intensity profile here, it is varying with the parameter, varying with the evolved sphere, the distance from the evolved sphere. And to cover that, here you can see we are, instead of considering a point, here we are considering a rod kind of structure, and that rod is known as rail rods. So due to these rail rods, though our evolved sphere is going through all these rods, so some rods evolved sphere is perfectly cutting, some rods evolved sphere is not able to cut perfectly. However, the diffractions, whichever rods the evolved sphere is not able to cut, so those from those diffraction spots we are getting very weak intensity. Okay, and this is the evolved sphere, and here this is the, you can see the evolved sphere, and these are the diffraction spot, and only Z, 2G, 3G, these will be the considered zero order Lave zone. So the diffraction, zero order Lave zone means the first layer at which the first layer at which the surface of the evolved sphere cuts the reciprocal lattice, that is the zero order Lave zone. Okay, and depending on the shape of the crystal that is diffracting, we will get in reciprocal space, we will get different. If it is a cube, if it is a cube like structure, that means the planes are like this. If it is, we are considering the planes are like this, then we will be getting a railroad kind of, the rod kind of structure. If we are considering that this is a sphere, we will be getting shells. If we are considering this is disc, we are getting some rod kind of structure. If we are, our crystal which is diffracting is rod, then we will get some disc and ring kind of structure. Okay, and yeah, then comes Kikuchi lines. So Kikuchi lines, we know that they are produced by inelastically scattered electron. What is the time now? Okay, I'll take 5-10 more minutes. So Kikuchi lines, we know that they are produced by inelastically scattered electron which can subsequently elastically scattered, and then the specimen should be thicker with less defects. That is also a criteria. And the Kikuchi line, as we have seen, one excess line will be there and another deficient line will be there. So, and in diffraction pattern, the bright line will be always from the farthest line from the origin, and the reason behind that we have seen it in scanning electron microscopy. Okay, that how the let's say this is if you remember, then this is the diffraction, it is happening, and then this is my screen. It is supposed to come in this direction, however this due to Bragg's angle it comes here, and then another set of plane is there, so it was supposed to go there, and this is, so this is the profile. And if you remember, we have drawn like this should be the ideal profile. Then due to this kind of, so this is IT, this is IS, so the intensity at point T, intensity at point S, and intensity at point T. So we should be ideally getting this profile, but due to the Bragg's diffraction, that means the inelastically scattered electron scatter once more elastically, then we will be getting some structure like this will be the intensity profile, okay, along 2 theta. So this is how we are getting a Kikuchi line. So yeah, this is the origin of the Kikuchi line. So first, when the incident electron is interacting with our specimen, the scattering happens. Scattering can happen from 0 to 360 degree. In all directions scattering can happen. Once the scattered electron comes in contact with another Bragg's plane and it gets diffracted elastically, then finally we will be getting two pair of lines will be getting. Those are called Kikuchi lines, or sometimes they are also called Kikuchi bands. Okay, and so why we will get this band kind of structure? We know that after scattering we are getting the scattering angle, the locus of the scattering, if we collect them around 3 dimension, then it will be a conical structure, right? So these are the two cones that I am talking about. That conical structure, the scattering will happen around in a 3 dimensions thing. But when that conical structure gets intersected by a Ewald sphere, so here this is an Ewald sphere. Why I have taken a rectangular? Because the Ewald sphere is too large. So when the conical section gets intersected by an Ewald sphere, then in that case a parabola will be forming. And since this parabola will be too large for us, because this parabola will be is in the order of 10 to the power like 10 or 12 meter in the order of that. So those two parabola, when we see it in a very small space, so those will be looking, so these will be originally two parabola, however in our small area they will be looking like band. Okay, so this is the origin of Kikuchi lines. And so yeah, so how do we index the Kikuchi lines? First, let's say we are taking this is just for your information I am saying. So this is we can take any of the diffraction pattern, and then so here let's say this is 0 to 0 point, and we can map the distance between them and perpendicular bisector. So let's say for this point the perpendicular bisector is this one and this one. So a line which is perpendicularly bisect this Z0 to 0, that will be one pair of Kikuchi line. Then the opposite to that one we can draw another Kikuchi line. So this Kikuchi line belongs to 200 minus 200. So similarly, now this is 0 0 0. Now we can add another Kikuchi line. How? We will make sure that this plus or minus 200 Kikuchi line does not move. Irrespective, we will rotate our crystal in such a way that this plus or minus 200 Kikuchi line will not move. Every other things will move based on the information, based on the angular information between all the lattice point. We will be adding one more. Let's say this we have added 111 Kikuchi line. Similarly, we know that between 001 and 101 pole, that means this direction, there will be an angle of 45 degree. So I'll rotate my Kikuchi line in such a, I'll rotate my crystal in such a way that the angle between this thing will be 45 degree, these two will be 45 degree. So like that I'll keep one Kikuchi line constant. Let's say this is plus or minus 200, I'm still, this thing is constant, and slowly after rotation I'll be adding. So this is one addition, this is another addition, this is another addition. So finally when I add all those, I rotate my crystal and add based on the angular information between different directions. When I add, I'll be getting a crystal structure, I'll be getting a Kikuchi line like this. So earlier this used to be manually indexed, but nowadays software index these Kikuchi lines. And here you can see one Kikuchi line corresponding to, this is an experimental Kikuchi line, and this is a theoretical Kikuchi lines that we have derived. And here you can see one bright spot, one dark spot, one bright spot, one dark spot. So this is how. So we are here currently, based on the rotation of the crystal, you can see where we are going. So first it was 000 and HKL, that means my first plane which I was going to see. Now 000 and then 2H, 2K, 2L. So based on the rotation I am going to see different Kikuchi line. So yes, so now coming to CBED, as I said, this CBED is nothing, convergent beam electron diffraction, and it is heavily dependent on L. L is the camera length. So here the L is decreasing actually. So as you decrease the L, if you increase the L, that means the magnification will be increasing. So L increase means the camera length increase means the magnification will be increasing. So once the magnification will be increasing, then what you will be able to see? You will be able to see. So this is the total bright zero means direct beam. It is not even the diffraction pattern. It is the only bright spot. So in this direction, L is decreasing. So once you decrease the L, then your magnification will decrease. So this is now the, all of this was zero order lavage zone. So this is the bright spot, and these spots correspond to some diffracted spots. Now when you decrease the L furthermore, then you can see these all are the zero order lavage zone, and then finally you will be able to see higher order lavage zone. So this is how we are able to get different even more information from our crystal. So here there are two scenarios, one is focused beam, another one is defocused beam. Sometimes in convergent beam electron diffraction we use the focused beam, as well as we also use the defocused beam. And defocused beam we use sometimes to get more information, so the focused beam will only give you information about reciprocal lattice, since it is only giving you diffracted spot, but the defocused beam will give you information about real lattice in real space plus reciprocal lattice. Okay, so this will so sometimes we do this kind of operation in CBED. So energy filtering also another thing that we do. Energy filtering means all the electrons after interaction with the sample will not be having same amount of energy. So that is why in CBED, convergent beam electron diffraction, we need to put some energy filter, and once we put those energy filter, you can see this is without filtering. And what I am looking at, so I am looking at, this is the direct beam. Okay, and without filtering. Here you can see with filtering. With filtering means we can see much more contrast, and we can see the position of the Kikuchi lines, and based on that we are able to extract much more information from our material. And yeah, this is the higher order lavage zone pattern that I was telling you about. So once you rotate the crystal, then you can see this are the zero order lavage zone, the first order lavage zone, and the second order lavage zone. So these are order of this the lavage zones, the diffraction spots are also related to S. S is nothing but the deviation parameter. Okay, and what is the correlation between the holes pattern or the Kikuchi lines? You see, if the zone axis is, let's say UBW, the beam is coming, first it is getting inelastically scattered, then it is getting elastically scattered. Here it will form Kikuchi line. However, if finally we are converging the beam at the beginning itself, it will be only elastically scattered, and then finally it will be forming Weiss-zone, both first order Weiss-zone, that means zero order Weiss-zone and higher order Weiss-zone. Okay, so yeah, I think we'll go through the questions quickly. So these are all conceptual questions. So one thing we could not go to in today's class is the contrast mechanism, which we will go through in the next class. So these are some of these questions which on conceptual questions. We can go through them quickly. Why are thin sections of specimen necessary in TEM? Can anyone answer? Electrons are negatively charged, have a wave nature, have no mass. Electrons have a poor penetrating power. Is anyone there?
Sir, D, sir.
Yes, electrons have poor penetrating power. So the penetrating power of electron is close to 100 nanometer. But we try to, when we try to put the sample in our specimen, we bring it to more or less 5 to 20 nanometer range. Okay, so there are different set of TM specimen preparation is there. I think we are going to study it in the next week. So yeah, the next question is which of the following statements is or are true? What should be done right after the TM column is shown to be evacuated? Insert the sample holder, further insert the sample holder, remove the dummy holder, shift the beam. So okay, anyone can guess? Anyone has, if anyone has worked in TM? Okay, this the means if you start working in TM, this there is a standard operating procedure we follow, SOP. Then according to that, so after the TM column is going to be evacuated, we remove the dummy holder. There will be a dummy holder will be there. Then we remove that, and then after that we insert the sample holder, because for the column, for the entire column to be evacuated, the chamber should be completely sealed, so there should not be any leakage should be there. So that is why, since we are inserting the, so let's say this is our TM column, and here it is the sample holder is there. So like this, the column is there. So this, there would be some since we are inserting the sample from inside, so this is the sample holder, so there should be some gap, should not be there. So to close that gap, we generally to close the gap, we put a dummy holder and then we close it, then we make it completely airtight. So the answer would be statement 3, shift the beam. We do not open the beam just after the evacuation. We increase the beam, let's say from 0 kV to 200 kV. We increase it in step by step, let's say 50, then 100, then 150, 160, 170, then 75, then we all the way we go to 120, 195, then slowly we go in this manner. So we do not open the beam till now. So shift the beam is not the correct answer. Insert the sample holder and further insert the sample holder are not the correct answer. So the option is C. What type of sample preparation is commonly required for TM imaging? Coating with a conductive layer, freezing the sample, embedding the sample in resin, thinning the sample to few nanometers. I think so coating with a conductive layer, it is done it in case of ACM, not in TM, right? So not in TM. Freezing the sample, no, this is not the correct answer. Embedding the sample in resin, no, this is also not the correct answer. We put it in resin, then we thin it down to a few nanometers. So this is the correct answer. The correct answer is D. So the following statement is true or false. You should turn off the light before examination of sample using the fluorescent screen. So this is also another standard operating procedure which has been written when you operate the TM instrument. So when we want to, when everything is set, that means we have inserted the sample into the sample chamber. We have our beam is high, and that means we have gone to the highest possible voltage of that instrument. Then for viewing of this instrument, for viewing of our sample, we turn off the light. Why we turn off the light? Otherwise it will damage the fluorescent screen. So there is a fluorescent screen associated with the TM where we see how our pattern is looking like. So if we keep on turning the light, then the fluorescent screen will get damaged. Okay, so this is the true answer. Okay, the following statement is true or false. TEM cannot be used to examine live specimen. True, false, none of these. So this TEM I am talking about is conventional TEM. So there are it is a, can anyone answer? True or false?
True, sir. True.
Okay. So this conventional TM we cannot use the live specimen. For that we need a separate TM, because live specimen means it's a biological sample. In biology, conventional TM means it is the beams are highly energetic, right? So beams are highly energetic. So once you put the highly energetic beam onto your sample, then it will be induced damage. The beam damage will happen, and you will not get the information that you are expecting. So for that we have we use separate type of instrument. So yeah, so conventional TM cannot be used to examine live specimen. So the following statement is true or false. We need to do the alignment of the electron gun, beam and rotation center every time we use the TM. So can anyone answer?
True.
True? No, it is false. The correct answer is false. So it is asking that we need to do the alignment of the electron gun. We need to align the electron beam. So this is the false statement that has been written here. We need to align the electron beam according to our requirement. But electron gun, it is fixed. So we do not change the alignment of the electron gun. We change the strength of the lenses, that how much deflection we want, how big the probe size we want. So based on that we change the strength of the lenses, so that our beam will be aligned with our sample. But the electron gun, it is we do not change the position of the electron gun. So every time we do not use it. So once something, let's say some damage has happened, then we change we open the electron that column, the TM column, then we inspect the electron gun, then we do the alignment. So every time we use the, because every time we use the TM we do not do that. Okay, the specimen requires the vacuum of the order of 10 to the minus 4 to minus 6 bar, 10 to the minus 4 to minus 6 millibar, 10 to the minus 9 to minus 12 bars, 10 to the minus 9 to 10 to the minus 12 millibar. So if you remember, the atmospheric pressure is 10 to the power 5 Pascal, that is 1 bar, right? And the TM vacuum minus 5 Pascal, that is how much? 10 to the power so this is how much? 10 to the power minus 10, right? 10 bar. Yes, so this is 10 to the power minus 10 bar. So 10 to the power minus 10 bar, 10 to the power 5, it's a 10 to the power minus 10 bar. If you are talking in that sense, so this is the atmospheric pressure, and this is the TM column. So 10 to the power minus 10 bar, so it will be how much? 10 to the power, so I think this one, 10 to the power minus 19 millibar. Now closest answer is this one is correct, right? 10 to the power 5 Pascal is 1 bar. I just check. Yes, this is correct. So this is 10 to the power 10 bar. So that means 10 to the power 10 bar is staying in this range, 10 to the power minus 19 to 10 to the power minus 12 bar, right? So C will be the correct answer. Okay, then the next question is, the Ewald sphere is smaller in X-ray diffraction as compared to electron diffraction in TM. We have discussed this so many times. Can anyone answer?
B, sir. False.
The Ewald sphere is smaller in X-ray diffraction. Yes, it is correct. So the X-ray it is the minus 10 to the power minus 9 to 10 to the power minus 11 meter. This is the the wavelength of X-ray. The wavelength of electron is in the order of, let's say, 4 picometer. So in the order of picometer we can consider. So the evolved sphere radius is will be 1 by lambda. So that means it is false. Kikuchi lines are formed due to inelastic scattering of the electrons within a crystal lattice. Can anyone answer?
B, sir, false.
Yes, it is false. It is not due to inelastic scattering. It is inelastic scattering followed by elastic scattering. So followed by elastic scattering. And I think this is the last question, the Harvey-Whelan equation. Okay, I don't think yeah, the Harvey-Whelan equation describes the variation is transmitted beam as a function of crystal thickness. We have not gone through in this class, but the lectures covered this one. Can anyone of you answer the Harvey-Whelan equation? So what does it describe about the variation in? So we'll see the Harvey-Whelan equation when we are going to see it in the contrast mechanism. So one of the contrast mechanism is diffraction contrast, right? I'm just telling. So this is diffraction contrast, and in the diffraction contrast, when we are talking about the how we can get the intensity of a diffracted point, and related to that we are going to get the amplitude of the diffracted point and the amplitude of the direct beam, amplitude of the diffracted beam and amplitude of the direct beam. We are going to get the Harvey-Whelan equation. So that means this is the amplitude, right? So I think that is the okay. So the fringe contrast we have not gone through. The specimen, okay, can anyone answer? If the specimen is dash, only spots will be seen in the diffraction pattern. If it is dash, then only Kikuchi lines will be seen. These are, I think the okay, I'll answer. The specimen is thin, then the spots will be seen in the diffraction pattern. Why? Because it will be diffracting, and if we can see the Kikuchi lines when our specimen is little bit thicker. So C is the answer. Convergent beam diffraction is also called as dash beam diffraction. So convergent beam diffraction is also called as macro diffraction. It is a large diffraction. It is not called macro diffraction. Femto diffraction. Femto means 10 to the power minus 15. So convergent beam electron diffraction does not give us resolution up to that level. So it is called as nano diffraction. So degree of scattering in transmission electron microscope is a function of dash, wavelength of the electron beam used, number and mass of atoms that lie in the electron path, mass of the sample. So can anyone answer?
Yes, sir.
Wavelength of the electron, no. Not only degree of scattering on a transmission electron microscope, it is number and mass of the sample. So the degree of scattering that will happen, it connects the number and mass of the atoms that lie in the electron path, not only the wavelength, because if you are not having a series like it is like the diffraction will not take place if you are not having any of the electrons, right? So based on the electrons in your Bragg plane, so the number of diffraction that is happening, then only you will be able to see whether the material the information that you are getting, whether it is sufficient for you to see, or you have to go to any other mode of operation. So we'll see this thing in the contrast mechanism, how these things affects. Okay, that is the end of the session.